Hello everyone, today we're going to be going over problem 10.3 from Fundamentals of Heat and Mass Transfer. The problem is quoted as such. It says the role of surface tension in bubble formation can be demonstrated by considering a spherical bubble of pure saturated vapor in mechanical and thermal equilibrium with its superheated liquid. We're asked to solve three problems. The first one is beginning with an appropriate free body diagram of the bubble, perform a force balance to obtain an expression for bubble radius, RB, is equal to 2 sigma over Psat minus PL, where Psat is the pressure of the saturated vapor and PL is the pressure of the superheated liquid outside the bubble. The next problem is on a PV diagram, represent the bubble and liquid states, discuss what changes in the conditions will cause a bubble to grow or collapse, and then finally, it wants us to calculate the bubble size under equilibrium conditions for which vapor is saturated at 101 degrees Celsius and the liquid pressure corresponds to a saturation temperature of 100 degrees Celsius. So for the first problem, our free body diagram is going to look like this. We're going to take a perfectly spherical bubble and we're actually going to cut it in half and just look at a hemisphere. And we can see that we have PL, which is our pressure of the liquid outside the bubble, as well as Psat, which is the pressure inside the bubble. And then our surface tension force is actually going to act on the circumference of this cut section through the middle. And so we can do a few force balances. So the first one is we're going to balance the pressure force. So we're going to say that our saturation pressure minus our liquid pressure outside is actually projected onto this cross-sectional area, which is going to be pi r squared. And then the force of surface tension can simply be written as sigma, which is a surface tension force, times 2 pi r, since it's acting on the circumference of that projected circle. If we set these equal, since we're assuming it's at equilibrium, we can set those two equations equal. We can do some rearrangement, and then finally we'll solve for r, which is going to be the radius of this bubble. So at equilibrium, the radius of the bubble is going to be equal to 2 sigma, or 2 times the surface tension, over Psat minus PL. So for the next problem, we're asked to look at a PV diagram and determine what conditions are going to change our bubble size. And so if we look at our PV diagram over here, we have one isotherm, so one line of constant temperature. And we'll start at a relatively high pressure. And as the pressure starts decreasing, we'll reach our first bubble point. And when we reach that bubble point, we'll start getting into the multi-phase. So we'll have both liquid and vapor. And that line is going to stay constant as the volume of the bubble grows at a constant pressure. And then our second point here is actually going to be our dew point, or our condensation point, as we continue dropping in pressure and the volume increases. So if we look at our equations here, we can actually rearrange our equation for P saturation, so the saturation temperature, and set that equal to PL plus 2 sigma over R. And we can look at two conditions. So the first one, if our Psat, or our saturation pressure, is greater than our liquid pressure plus 2 sigma over R, then our bubble is actually going to grow. So we're actually going to move right on this diagram and our volume is going to increase. And then in the same way, if our saturation temperature is lower than the pressure of the liquid plus 2 sigma over R, then our bubble is actually going to decrease and we're going to have bubble collapse. So we're going to move leftwards on the PV diagram. And so finally, we're asked to solve for a bubble radius at a hypothetical situation. So we're given that the temperature, or the saturation temperature, is 101 degrees Celsius, and the temperature of the superheated liquid is 100 degrees Celsius. And we can look up actually the surface tension of water at these conditions, which is approximately 0.0589 Newton per meter. And then we can actually go from the steam table, which is provided in the textbook, and we can determine what our pressures are at our two temperatures. So our PL is actually going to be 1 atmosphere of 101.325 kPa. And our saturation temperature at 101 degrees Celsius is going to be 105.3 kPa. So we can use our Laplace pressure equation that we determined earlier, where we have R is equal to 2 sigma over Psat minus PL. We can plug in all of our numbers and we'll come up with an approximate bubble radius at equilibrium of 29.635 micron. So a very small bubble.